Welcome to Tennessee's at-home learning series for math. Today's lesson is for all our 8th graders out there, though all students are welcome to tune in. Today's lesson is going to be the 6th in our series. My name is Candace Thompson, and I'm an 8th grade math teacher at Oakland Middle School in the Rutherford County School System. I'm so excited to be your teacher today. Welcome to my virtual classroom. If you didn't see our previous lessons, you can find them on the Tennessee Department of Education website at www.tn.gov/education. If you don't already have the student packet for this lesson, you can find it online in the same place. And I actually have that link pulled up for you here. So you can tune in and find all of not only our schedule for when our lessons will show, but you can also click down here where it says resources, student packets, and teacher lesson plans. Today we will be learning using functions to model linear relationships in mathematics. Before we get started, to participate fully in our lesson today, you will need the following: paper, pencil, and a hard surface to write on. A calculator is not required, but it may be used to check your calculations. And then optional, but it will be helpful, is if you have any graph paper available. Okay, so do you like pizza? I know I do. What is your favorite pizza topping? Do you like cheese? Do you like pepperoni? Do you like pineapple? Did you know that the most common pizza toppings in the United States are pepperoni, mushrooms, onions, sausage, bacon, and extra cheese? We're going to start today by exploring some situations that can be modeled by a linear function, like the cost of pizza depending on the number of toppings. Here are a couple of things we need to remember in today's lesson. First, y equals mx plus b is the slope-intercept form of an equation, where m represents the rate of change or slope of the equation or function, and b represents the constant or initial value. What I tell my students is the initial value is the value of y when x is 0. The point b is also the y-intercept when represented graphically. The equation can be stated: the variable y is a function of the variable x. Identifying the rate of change and the initial value in the description of a linear situation can help you construct a linear function to model the situation. Are you ready to begin? Okay, let's get started by reviewing some things you've already learned. At this point, I'm going to go off of the screen so I can pull up some of the equations and visuals we will be working with. So first, let's look at these 4 equations I have written down. Which of these two have the same slope or the same rate of change? You're right. A and B both have a slope or a rate of change of 2. Which ones have a negative slope? You're right again, C and D, because C has a slope of -5 and D has a slope of -1. Sometimes not having a coefficient in front of this variable x confuses some of my students, but what I always tell them is if you see x by itself in this situation, the slope is understood to be 1. Okay, now let's focus on the y-intercepts or initial value. Which of these equations have the same y-intercept or the same initial value? Great. Both A and C have a y-intercept or an initial value of +1. Let's look at a couple of more examples. So here are 3 more that I want you to look at. Which equation is in slope-intercept form? Right, only A is in slope-intercept form. And I have a little note for you at the top that slope-intercept form is the same as just saying y equals mx plus b. So only A is in slope-intercept form. What would we need to do to equation B to get it into slope-intercept form? What would we need to do to this equation to get it into slope-intercept form? Well, if you notice, I almost have it in slope-intercept form. The only problem is this coefficient 3. So if I divide each term by 3, I now have it in slope-intercept form. 12 divided by 3 is 4, so I have a slope of 4. And 21 divided by 3 is 7, so I have a y-intercept or an initial value of 7. Okay, now let's focus on equation C right here. What would we need to do to get this in slope-intercept form? Right, so our issue here is that we need to move this term 4x over to the other side. So what I can do, I'm going to rewrite the equation. 4x plus y equals 100. I need to move this term 4x over to the other side. Now, if I do that, I've got to do the inverse. So right now, this is a positive 4x. To move it to the other side, I'm going to subtract 4x. So I have y equals, now I cannot subtract 100 minus 4x. They are not the same terms. So I can write this as negative 4x plus 100 if you want to put it in y equals mx plus b form like we have here. But it would not make any difference if you put 100 minus 4x. Just make sure that negative 4 remains a negative 4 and that positive 100 remains a positive 100 if you choose to write it that way. Okay, now let's explore a graph to see if we can get the slope-intercept form from a graph. Let's take a look at this graph here. Okay, what can we see? What is the y-intercept of the graph, or the value of y when x is 0? I hope you could see that the value of y when x is 0 is 1. So here is our y-intercept. What about the rate of change, or the slope, from one point to the next? How far up and how far over do you have to go? So what I always tell my students, when you're trying to find the slope of a line or the rise over run, you want to find 2 points that go perfectly through the grid. So the y-intercept is always going to be 1 point. Do you see how this point doesn't hit perfectly through the grid? I want it to hit right here on the corner of a square somewhere. And this isn't perfectly through the grid. Right here is perfectly through the grid. So now what we're going to do to calculate the slope is we're going to calculate the rise. So I rise up 1 unit. Now we're going to calculate the run. 1, 2, 3 units. And so my slope is equal to my rise over run, which in this situation is equal to 1 over 3. And remember earlier, this green point, that represents my y-intercept, and that is positive 1. Now let's write an equation in y equals mx plus b form, or slope-intercept form, where you will remember that b is the constant or initial value on a graph, and where the line crosses the y-axis, and m is the rate of change or the slope of a graph. Give it a try and see if you can write an equation for this graph. Does your equation look like this? Y equals 1/3 x plus 1. Great job. You will have a problem like this to solve on your own for independent practice today. Now let's go back to our conversation about pizza. Let's think of a local pizza shop that sells pizzas like this. A customer can use this menu to call in a pizza order. The customer will choose a size and add toppings. The graphs and equation models the price of the 2 sizes of pizza. Remember to define your variables. Let x be the number of toppings. So I'll write you a note here. We're going to let x be the number of toppings. And we are going to let y be the total cost of pizza. Okay, so if we look at a small pizza, okay, and remember, we want to use this to write an equation in slope-intercept form. So y equals mx plus b, okay? So if x is the number of toppings, what's going to go right here is how much they're charging per topping. So for a small pizza, how much do they charge per topping? Correct, they charge $1.50. So I have y equals 1.5x. Now, remember, this is going to represent how much the pizza is regardless of how many toppings you have. So how much is a small pizza? It's $8. So if I were to write an equation for a small pizza, it would look like this. And I'll highlight these two for you. So a small pizza, an equation for that would be y equals 1.5x plus 8. Okay, now let's see if we can use this same logic and write ourselves an equation for a large pizza. Okay, so remember, it says that x is the number of toppings. How much does a large pizza, how much do the toppings cost? Correct, they cost $2, so that's going to be my rate. And then how much is a large pizza before any toppings go on it, when the toppings are 0? $12. Good. So this equation in yellow represents the cost of a large pizza. That's going to be the equation we use. Okay, now let's look at a graphical model of these two equations. Which line represents the price of a large pizza? Right, line A does, right here. This is line A. This represents the price of a large pizza. If you notice, the initial value, or the y-intercept, is 12. And for every one topping, the price increases by 2. So if you look here, here are my number of toppings. So for one topping, when toppings are 1, the price increases by 2. It goes from 12 to 14. Okay, if I have 2 toppings, since each topping is $2, it should increase by 4. So it goes from $12 to $16. Okay, great. So which form do you prefer? The equation, like we just worked on from these tables, or the graphical model? Good thinking. No matter what you prefer, if you know how they are connected, then you can easily convert your work between the two. However, you might notice that the graph might require more estimation than the equation if we were just reading it. Let's work together on answering some additional questions. Which equation and graph represent the price of each size of pizza, and how do you know? So let's go back to our equations here. Here we go. So I'll ask my question again. Which equation and graph represent the price of each size of pizza, and how do you know? The graphs and equations are linear models because they model or represent linear functions. If a linear function has a constant rate of change, what do the rates of change represent in this situation? What did you decide? The rate of change is the cost of each additional topping. The initial value of each function is the value of y when x is 0. What do the initial values represent in this situation? So what do these initial values here, here, or if you're looking at the graphical model, here and here, what do they represent in this situation? Right. That is the price of pizza with no toppings. What quantities do the variables X and Y represent in this situation? Let me help you out a little bit with this one. Let's see if you can fill in the blanks. And if you want to take time to copy that, you can. So X represents number of, I want you to fill in this blank here. Y represents the total blank of a blank. And then the total blank of a blank is a function of the number blank. Did you fill in something like this? So you should have filled in X represents the number of toppings. Y represents the total cost, or you could have put price of a pizza. The total cost or price of a pizza is a function of the number of toppings. Great. Did you know that some people think that the graph or equation can only tell you the cost of the pizza? However, if you know the total cost of the pizza, you can also find out the number of toppings that you should have as well. Want to try that? Of course you do. Let's give this a whirl. If Andrea spent $9.50 on a small pizza, so $9.50 on a small pizza, how many toppings did she get? So I want to remind you that the equation we used to represent a small pizza was y equals 1.5x, and I'll write that out to this side for you. Y equals 1.5x plus 8. So if Andrea spent $9.50 on a small pizza, I want to see if you can determine how many toppings she got. So you can use the equation here, or you can use the graphical model. Remember that this line, line B, represents the small pizza. And I want to know how many toppings she got if she spent $9.50. Did you figure out that she has one topping? Did you use the equation or the graphical model for your understanding of the problem to figure it out? So if I have one topping, it's going to be somewhere up here. Or I can plug it into the equation. So I have y equals 1.5 times the number of toppings plus 8, and I get $9.50. So either way, either representation is fine. Here's another situation. If Mitch spends $18 on a large pizza, so let's go to here. So if Mitch spends $18 on a large pizza, and remember our equation for a large pizza was y equals 2x plus 12, okay? And if you're using the graph, that green line is going to represent our large pizza. So if he spends $18 on a large pizza, how many toppings did he get? Okay, so did you figure out that if the pizza costs $12, no matter how many toppings he gets, if the pizza costs $12, no matter how many toppings he gets, and each additional topping is $2 on the large pizza. Then Mitch got 3 toppings. Let's look at the graph. So I'm going to look for when this is 18. And you see right here, and the number of toppings would be in between 2 and 4, which would be 3. Or I could use the equation y equals 2 times the number of toppings, which is 3, plus 12. Y equals 6 plus 12. Y equals 18. All right, terrific work today, students. Today we explored using functions to model linear relationships in mathematics. I hope you are making connections between the linear equation and the graphical representation of the functions we are modeling. After this lesson, you will have a few problems to practice on your own. I will show you the independent practice problems now, or you can find them on the student practice for this lesson on our website, the www.tn.gov/education. All right, guys, so I'm going to pull up our practice problems that are available on the website. I'm going to let you guys go through number 1 on your own. This is just a simple Frere model that you can fill out as you're thinking about all that we talked about today. We're actually going to move on to number 3 and kind of work that out together. If at any point I'm going at a faster pace than you would like to go, please feel free to pause this video. So number 3 says a poster announces a carnival is coming to town. People pay an admission fee to enter the carnival. Then they buy tickets to go on rides. The total cost of attending the carnival is a function of the number of tickets bought. The graphs and equations model the total cost for children and adults. So we have the equation y equals 1.25x plus 10, and it looks like that represents adults. And then we have y equals 0.05x plus 5, and it looks like that represents children. So kind of answered our first question. Which equation and which line model the total cost for a child, and how do you know? So let's go back and read. We know that the total cost, I'm going to underline this, the total cost of attending the carnival is a function of the number of tickets bought. So remember, when we were first introducing it, the variable y is a function of variable x. So if the number of tickets bought, what are they charging per ticket with the children? They're charging 0.75. Okay, so I know that this equation, y equals 0.75x plus 5, this is going to represent the total cost for a child. I'm going to multiply 75 cents times however many children's tickets I buy, and then I'm going to add on $5 to that because that's the initial cost for a child, to enter the carnival. So now I've got to look at this graph. What would be a very easy indicator to identify which of these lines represents my function? So the easiest way to identify this equation on this graph would be to use the y-intercept, or the value of y when x is 0. So I know that whichever line has a y-intercept of 5, that is going to be the line that represents the cost of a child's ticket, and that would be equation B. It's kind of hard to see on my screen, but if you have this packet pulled up or printed off, you're able to easily see that. And then we should also see a slope of 0.75. And if you want, you can check that on your own. So let's answer question B. It says, which equation and line model the total cost for an adult? And how do you know? So we're going to use the same logic. The variable y is a function of the variable x. So the variable y, what is my y variable? One way that you can identify this is you can look at what the y-axis is labeled on the graph. So in other words, the variable y, or the total cost, is a function of the variable x. I look at my x-axis and I see that it's labeled as number of tickets. So the total cost is a function of the number of tickets. Well, for an adult, I know that the total cost is going to be, it tells me $1.25 per ticket plus a $10 admission fee. And I can use my same logic I did as before, in that I'm going to figure out which line represents the adult's cost by seeing which line has a y-intercept of 10. And as you can see, line A, or the one that I'm about to highlight in pink, has a y-intercept of 10. All right, guys, I enjoyed reviewing using functions to model linear relationships in mathematics with you today. Thank you so much for inviting me into your home. I look forward to seeing you in our next lesson at Tennessee's At Home Learning Series. Goodbye.